part of what is helping these cells down this pathway or down this maturation process is interaction with stromal cells of the bone marrow, in this case, similar to what we saw in the thymus. Okay, so here's that earlier part where we start with those hematopoietic stem cells, and then through a series of steps, they become more and more differentiated until we get to the point where we get to the common lymphoid precursor cell, that same cell that we talked about with T cell maturation. So this cell can become either T or predominantly T cells or B cells, although they can also become NK cells and dendritic cells too, but we're going to focus on the lymphoid part of that. So if these cells leave the bone marrow, go to the thymus, they become T cells, of course. The ones that stay in the bone marrow become, or at least begin to become B cells. They enter the pre-pro B cell stage. And then we looked through the later stages, focusing mostly on what's happening inside the cell in terms of the rearrangement of and expression of the B cell receptor of the membrane-bound immunoglobulin. It can also be traced using these cell surface proteins, but I'm not really interested in memorizing that pattern. I don't think that's, for us, that's not the important part. The important part is what's happening inside in terms of that stepwise process with rearrangement of the immunoglobulin genes, expression of the heavy chain along with the surrogate light chain, that pre-B cell receptor that then sort of triggers the completion of the rearrangement with the light chain, and then we finally get full expression of the real IgM on the surface of these immature B cells. So again, we're also using sort of the more commonly used terms, the pre-pro, early pro, late pro, rather than these ABC, DC prime things. I think most people use the other phrases. Okay, and as usual, all of this is ultimately a result of various signals being received through various receptors, activating various transcription factors that are turning on specific sets of genes to allow this progression through these stages of maturation. Okay, so we saw that then those immature B cells are going to leave the bone marrow, head to early on to the spleen, and go through those transitional stages T1 and T2. And again, can be marked by changes in expression of these cell surface markers. On the outside, we sort of looked at it, again, especially as a result of sort of the second round of selection in the periphery. So the selection that happened back in the bone marrow is usually referred to as central tolerance. We saw that in the periphery, this leads to peripheral tolerance. So it's a second, sort of a second layer of selection, for the most part, negative selection to get rid of self-reactive B cells. The difference here, we didn't see this to this extent in the thymus, because remember, we have that special transcription factor, that AIRE, A-I-R-E, that allowed the thymus to pretty much express every known protein. You don't see that in the bone marrow, so this peripheral selection is also important to get rid of any residual autoreactive B cells. So we have another round of negative selection that gets you apoptosis if they react with self-proteins. And this positive selection is really, in a sense, the activation of these B cells into this B2 situation. Okay, so that's the difference between T1 and T2 cells. Along with some other, we can take a look. I don't think we took a look at this last time. So there are other characteristics of these transitions from T1 to T2 to mature that you can see here in terms of formation of lipid rafts, those specialized sections of the cell membrane where all of these B cell receptor molecules sort of aggregate. Calcium concentration has to do with certain signal transduction pathways. Diacylglycerol, if you remember that from Bio 230, is part of the phospholipase C transduction pathway. The BCL-XL is one of those families of those sort of accessory proteins that control the pores in the mitochondria that either let out or don't let out the cytochrome C. That particular one does not let it out, so it's an anti-apoptotic peptide, which means, in other words, sort of a pro-survival signal, so that increases as these B cells mature, and the ability to induce apoptosis decreases, so both of these together help to ensure the survival of these mature B cells. So that's essentially, I think, where we got to last time. How are we feeling about B cell development and maturation? Okay. Okay, there's actually not too much to finish up this chapter. So, in case I wasn't stressing it last time, we really have focused on what's called the B2 B cells. Again, the traditional kind of B cell that do exactly what we think they do, get activated and make differentiate into plasma cells, more on that in a couple of chapters, and make antibody. But there are, or have relatively recently been identified a couple of other lineages of B cells. One of them is called the B1 B cells, and we'll also look briefly at these marginal zone B cells. So differences seem to be in part where you find them and sort of their antibody repertoire. So we'll start with these B1 cells. These more resemble what you would expect from an innate immune response, in that these B1 cells have a limited repertoire of membrane-bound antibody that's mostly against microbial carbohydrate antigens, as it turns out. So they much more resemble something that innate cells look for, right? Carbohydrate patterns that are always other. And they have, through perhaps some kind of selection process, it's kind of unclear what limits their immunoglobulin repertoire, but they make antibodies mostly against that type of antigen, and some people refer to those antibodies as natural antibodies. Interesting term. And most of these are against microbial carbohydrates. Like I said, in that sense, sort of thematically, they seem to, look more like part of the innate system. They are now thought to be self-renewing and are essentially a separate lineage of B cells. So the story is not complete. But rather than, the normal B, I shouldn't say normal, B2 B cells, regular old B cells, keep coming out of the bone marrow. These B1 B cells, it would seem, once they're made and established, it's a self-renewing population. Okay, so new ones are not always being made, which is kind of weird. And again, restricted diversity, mostly against those microbial carbohydrates. You don't get any somatic hypermutation. I think we've talked about that a little bit. We'll talk about that more once we get to the antibody response. That is the situation where you get those mutations, usually in the antigen binding sections of the antibody during the course of an immune response. They don't seem to need help from T cells, so they kind of act on their own. Again, much more like innate cells do. More IgM than IgG. Again, majorly against carbohydrates. Again, more like the innate system, little or no memory. And what's that last one? Surface IgD. Okay, so little or no surface IgD, which also really distinguishes them from B2 cells, which have both on the surface. That's one of the defining characteristics, right, of the B2 B cells, so it's expressing both isotypes. So they are kind of a neat, interesting group of cells. And I think I skipped over it, sorry. The major sites, rather than being in the traditional secondary lymphoid organs, spleen, lymph nodes, whatever, we find these mostly in the peritoneal cavity, in your abdominal cavity, and the pleural cavity, or around the lungs. So they are sort of specialized in that sense as well into those particular anatomical niches. So they seem, like I said, to represent kind of a unique lineage, a distinct lineage from the B2 cells, but we certainly don't understand completely exactly how all that is set up differently. So they're out there. And then this third group has also been identified, although these seem to be more closely related to, at least maturationally, to the regular B2 B cells, are these so-called marginal zone B cells, named for their major place of location, the marginal zones of the spleen. Okay, so just to remind you, the marginal zone is sort of the outer most layer of the spleen. Again, long-lived, they may be self-renewing. I think there's not enough evidence yet to really make that distinction. Again, a much more limited repertoire, okay, and what exactly is doing that limitation is not understood. Is it a selection process? Is it some additional step or control over recombination of the immunoglobulin genes? I don't think is known yet. Varied amounts, so they may or may not need T helper cell help, express both IgM and IgG, although not in the same amounts. Again, these seem to be, again, sort of on that border, that cusp between the innate and the adaptive system. So they respond to carbohydrates, but also to proteins. Don't know much about the memory, and little or no IgD, so that again distinguishes both of these types from the traditional B2 kind of B cell. But these are thought to be at least more linked maturationally to the follicular cells. They're thought to derive from the T2 population. So after it's gone through the sort of peripheral selection, these two T2 cells, probably most of them mature into B2 cells, but some of them apparently mature into these marginal zones and sort of stay in the spleen rather than starting to circulate like follicular B cells do. So there are these couple of other categories of B cells that are out there, so it's worth mentioning, it's worth knowing a little bit about them, or what little we do know about them. We'll obviously spend most of the rest of our time talking about the traditional B2 B cells. So I'm sure lots more work is going to be done on those other populations to really ferret out, some of what's doing this restricted diversity or what's causing that. Especially, that's I think an important question. And yeah, I left the big table in, but we'll do the smaller tables. So the final table is kind of a good one to kind of just walk through in terms of comparing chapters 9 and 10 basically to each other. So B cell development and T cell development. Just kind of comparing, contrasting, so there are lots of similarities. So, oh, that's going to be really fun for the next 6 months. So obviously, all of these cells start from that same common lymphoid progenitor cell in the bone marrow. Obviously, only T cells go to the thymus, whereas B cells finish their maturation, most of their maturation in the bone marrow. Both have heavy chain or heavy chain equivalent, heavy chain or beta chain recombination goes first in a two-step process. So that's pretty much identical between the two. The heavy chain or the beta chain of the T cell is expressed with the surrogate form of the light chain. That happens in both, and that then signals rearrangement of the real light chain. Okay. We also get a proliferative step, right? Beta chain or heavy chain proliferation. The light chain or the equivalent has only B and J segments. That's the same. Signaling through the real completed receptors necessary for survival. That's true for both. There is some form of positive selection is true for both, but the details are different. So sort of plus minus, it seems more true for the B1 subset than the B2 subset. But and of course, positive selection is a major step in T cell maturation. It is true that both have some ability to modify that chain editing we talked about. You sort of get that second chance if you first made a self-reactive receptor, although it seems more important to the life of a B cell than a T cell. Negative selection gets rid of autoreactive cells. That's true for both. But the difference is sort of where that happens and to the extent that that happens. So it's ectopic expression of autoantigens is definitely there's that ARI protein that we talked about. So that's more prevalent in T cells than for B cells. MHC recognition is involved, is only for T cells. Allelic exclusion obviously applies to both, especially for the heavy chain, a little bit more fluky if you remember for the light chain in terms, well, really not the light chain, but for the alpha chain of the T cell receptor, the allelic exclusion is a little more leaky. And then both had the result of a loss of a majority of cells, and development completion in the periphery is also true for both. So there's actually more similarities than differences, in the broad thematic scheme of things. Obviously, there's a lot of differences in the details of the different stages of T cell and B cell development, but thematically, there's a lot of similarity in it, and I hope at this point that's not too surprising. They both come from the same common cell type. They're both creating receptors that do fundamentally similar things. What they exactly do is obviously different, but thematically what they're doing is the same, so I don't think it should be too surprising to find that the overall development of these two lines of cells is more similar than different. I hope that's not too surprising when you saw that. So probably worth, these also hit kind of the big themes, so I think this table is probably a good one to kind of walk through a couple of times before the exam and see the similarities and differences. I think would be a good idea. Okay, so I think we're going to do a short day because that's already annoying me.
They do for so early in the morning, but they do nothing early in the morning, and then when classes start, they start doing work.
Well, they're supposed to be doing the bulk of it overnight.
Yeah, I know.
That's clearly.
We got here really early on Wednesday morning, and they were just walking around pointing and talking. There was no work to be done.
Yeah, well, that's part of what low bid processes get you.
Yeah.
I didn't say that. Okay, let's see.
Yeah, they were just sitting around.
So I think we have one more chapter to go. So chapter 11 will be on the next test, so it'll be 8, 9, 10, 11, is that right? Okay. Okay, so we have one more chapter to go. We'll go back to T cells. We're kind of bebopping back and forth between T cells and B cells. The next chapter for T cells